Begin.
Hello. I'm going to talk about mutation testing, theory and practice. So, start with an agenda. I'm going to talk what is mutation testing at all, how does it work, how do you use it, whitelisting is an important topic, what kind of mutations does the mutation testing do, some limitations, summary, questions, and live demo, hopefully. So, what is mutation testing? So, it took me a really long time to really get my head around it. So there's a lot of different ways to think about it. So you hear people say stuff like, if the test succeeds, it fails. And I'm like, what? I don't understand. It's very confusing. So I'll try to explain this in a way that you hopefully haven't heard before and that makes it click. I think it's a useful way of thinking about it. So let's say you have a library. You built it from scratch. You've made a bunch of releases. You've used it in some projects. You've got 100% test coverage, right? Even maybe 100% branch coverage, right? You're very proud. It's hard to get right. It's very hard to do. But what if I told you there's some other code base that's not your code base, but it passes all of your tests, right? That doesn't feel good. You have 100% test coverage. So then what if I told you I have hundreds of those code bases and I switched your code to one of them? They might be broken, they might be okay-ish, right? But you can't tell. So if you can't do a git diff at this point, you might panic. So this is a good way of thinking about mutation testing. It's finding all of these and finding out why does my tests pass when it's not my code anymore, right? So I'm going to talk about Mutation, which is the mutation testing system I've written. So when I first wanted to try mutation testing, I tested first the big name, which is Cosmic Ray. I was very, very dissatisfied. I couldn't even get it to install on my machine. It's gotten better since I complained to them a lot. And then I tried another one, an old project called Mutation, which is like a PhD student thing, and I tried to refactor it, and after a few hours I got sick of that and said, I'll just write my own. So I did. This is the best one, obviously. By far, it has some really nice features I'll go through later that makes it like amazingly better in the UX department. So, how does it work? So, in the theoretical realm, of course, the name is a hint, obviously. We introduce mutants to the code base. So, a mutation or a mutant is a change to the code that should change your behavior. But if it should change your behavior, if your tests don't fail when I change the behavior of your code, you have a hole in your test suite, right? And if you're not really careful with your tests, you're going to have tons of these, like every edge case, every boundary condition, everything. And there's much more than that. So maybe that's fine, maybe your code is correct now, but you introduce an off by one error when you refactor later, and you won't catch it because you don't check your boundary conditions. So let's think of the absolute simplest mutation you can think about, a comparison operator. So if foo is less than bar, you call buzz. Simple, right? But will your test suite really break if I change it to this? Maybe. Right? You probably have some tests that wouldn't detect the change like this. So, mutation testing is about changing your code in some nasty and probably very subtle way, and then we run the test suite again. So, then it's of course not running your code again, it's running the mutated one. So your test suite should fail, right? So that's why they say if it passes, it fails. That's the weird thing about that. So, and if that happens, you have a surviving mutant. That's what we call it. So we do this systematically for every place in the code base that can have a mutation point, which is what we call it. It's a place where you can semantically tweak the code and get a different behavior, or maybe a different behavior. So I'm going to say on average, you probably have like 1 mutant every other line. So some lines will have 10 mutants, or maybe 5, like a lot. And many of them will have none, or 1. So this is what it looks like to run new mutmut. You do pip install mutmut and the mutmut run, and it comes with a little bit of a explanation for you. So this is an actual library we have in here, proprietary. So this is not a GitHub library, but you can see we have 39 killed mutants. This is good. No timeouts. This is also good. No suspiciously running things, but we have 17 not so happy mutants surviving. So you want to kill those by fixing your tests. Right? So obviously someone is thinking, this seems slow, very, very slow, right? Yeah, and it is. It's very slow. In the trivial case, in mutmut, we rerun the entire test suite to kill a mutant, right? So if one test fails, then that's it. So you can stop early. So that speeds it up a little bit, but not much. It's only, yeah, it's not so good. So it's going to be very, very slow. You're going to run your entire test suite one time for each mutation point in the code base, which can be hundreds, thousands, tens of thousands if it's a big code base, right? So it doesn't scale very nicely if you don't know which test to run. And I have no support for that. But I do have some other ways to alleviate this problem. I keep a cache of which mutants have been killed and which ones are alive. I know if you changed your code or not, and if I changed your tests. So actually per line I can know this line is now untested. I can rerun the surviving mutants on that, and if I assume that if you kill the mutant, it's going to be stayed killed. So yeah, if you delete your tests, well, you're on your own, right? And you can, if you're working on one mutant, you can rerun your test suite for that one, which is very handy when you're working through your code base. And you can just start it. You get a few of the surviving mutants, you Control-C out of it, and stop it, and you can work on the ones you found. You can even go into another, while it's running, go in and check on the results live, because it's a nice database. So it's very nice. So we're going to talk about prerequisites. So 100% code coverage is a soft prerequisite, right? You will get a lot more benefit out of your test suite by first working just by coverage data, because you're going to find actual bugs by actually going to 100% test coverage. Mutation testing, we found very few actual bugs by this, but we're very careful. We're very sure we're not going to introduce new bugs in the future. But it's a soft prerequisite, because getting to 100% test coverage by just looking at the coverage lines is kind of frustrating and awkward, right? It's like, oh, I have to figure out why I have to hit this thing, and I have to go into this. But if you do it with mutation testing, it's every single step is super obvious. I mean, it's much more clear. It's like this point here, I have to fix that. So it can be sort of easier to work with, because it's every step is smaller and simpler than, you know, I have just some lines that are uncovered. So it could work even if you don't have 100% test coverage from the beginning. So you found some mutants. What's next, right? Mutant is based on a library called Parcel, which is an AST manipulation library that is round trippable, which means that it keeps all your formatting. You go to the AST, you fiddle with it, you write it back. You won't lose your comments, you won't lose your new lines, which is very nice. That also means that all my mutations that I perform can be applied on disk without destroying your code base. My competitors don't do that, right? And this is really nice when working on one. You have a mutant and you apply it on disk, and you can see the code change, and you can see that your tests they're still passing. And you can write a test that's not passing. You revert thing, it passes, everything is good, right? It's very nice to work with. The other mutation testers, they supply you a diff of what the mutant is, but it's a diff of not your code and the mutated version of not your code. Like you take the AST, you throw out all your formatting, all the comments, and then they mutate that, and then just show you a diff. I was like, here, it's not your code, but it's kind of, if you squint, you can kind of see it. It's really hard to find it in your code base. But this is, right? Yeah, you can also tell Mutant to show you a mutant as a diff directly, like a patch output. Sometimes that's enough to work with it, and you can tell it to run that one, so you can work it like that. So some mutants are real problems in your test suite. So like this, like you should have found that. But sometimes it's not real things that it finds. So then you'll have to whitelist them. So let's look at some examples. This, for example, is the first thing it's going to find in your lib, because it's the first line, most likely. It's going to mutate that string and say, I changed your version string to XX030XX, and your tests didn't know this. I'm like, yeah, they shouldn't, right? So you need to whitelist that. This thing, the 0 is the nasty, no, the 1. The 1 is the nasty one, right? If you change that to 2, this does the same thing. This is an optimization. But if you whitelist that thing, it's going to whitelist the mutation of that, and that, and that. So that's not so good. You want to change that to partition. If you haven't used partition, look it up. And that's what you want to do there. This is the nasty part. It's going to mutate break into continue, which is really nasty in some specific cases. So you're going through a list and you found the thing you're looking for, right? You break out of it. But if you just continue, it's fine. It's fine. You save the thing you wanted to look for somewhere, and it's not existing anywhere else in the list. It's just going to be slow, right? So you want to whitelist that. This one is a fun one. We have a cache key, and it needs to be something, but you use the same variable lower down. So it's always going to be the same. It's always going to match, and it doesn't matter what it is. It just needs to be the same in the start. It's going to be the same. So you need to whitelist those things too. Reppers, who cares? It's just for the programmer. You can whitelist them. So how do you whitelist stuff? Well, you just do that. Pragma no mutate on the line. It's similar to how you do it in coverage, but this is only per line. You can't do it on an entire block, which is it's like already whitelisting an entire line for mutation testing is already a bit of a big hammer, right? Mutating like saying I'm going to whitelist an entire class is going to be not good. So what kind of mutations does Mutant do? It modifies literals like strings, dicts, and integers. It's going to change your keys in your dict literals. It's going to increment all your integers by 1 if you have them hard-coded in your code. It's going to say all your variable assignments. It's going to say your foo equals some bar. It's going to say foo equals none. And your tests will very often just say, okay, that's fine. Like, why? Removing arguments to function calls is a fun one, and a lot more. And since Python is, of course, dynamically typed, you can do a lot of things that other languages won't let you do. And this is the list of just straight from the source code. This is what we do with operators. So, plus, change for minus, minus to plus. Yeah, power of to just multiplication. Maybe you just tested something where power of and multiplication actually has the same results. Probably, maybe. And so forth, right? So, summary. So it's clearly not. I mean, mutation testing has made us feel a lot more comfortable in our test suite. We have a lot more tests. We test real things that we should be guaranteeing about the behavior of our library. But obviously it's not a panacea. We haven't found a lot of bugs, a few, but not a lot. You probably want to start out with some tests manually written before, because it's just a pain to get started with mutation testing from scratch. And it just won't find certain bugs. So you might need property-based testing, maybe, or maybe even formal verification if it's something really, really business critical or math heavy. So, is it worth it? Drum roll, probably no. So you probably won't run it on your big thing. Right? We can't. Like, if you have a test suite that takes 40 minutes, you can't do that. That's not feasible. If you can cut down the number of tests you want to run, and you know what they should be doing, you can run it on certain business critical parts. But sometimes the answer is absolutely yes. If you have a fairly small foundational library used all over your product, like we do try-struct, for example, I've done mutation testing on. This is really a good place to do it. The tests are fast, they're small. Going through a full run isn't it's not so much work, and you'll end up happier at the end.
How long does it take to run?
So I'm going to do a live demo.
Yeah, I mean, without mutation, just running the test suite once.
For try-struct?
Yeah.
Oh, it's like, I don't know, 0.2 seconds, 1, something. It's very quick. It's longer now after mutation testing. That's also a funny thing, because you're adding tests, right? So it's getting slower as you're approaching the goal, which is kind of demoralizing, but that's the way it is.
No, also in try-struct we have 2 implementations.
Yeah.
We see implementation, so you get more bang for the buck when you have 2 code bases with the same test suite.
Which is also a bit scary, because I don't mutate the C code, but I do mutate all the behavior in the Python code, and then we have a C implementation, and we run the Python tests against the C implementation, which feels a lot better. Yeah, and I want to talk about, there's a strange little, I don't know, side effect or something about mutation testing, which is it creates, it's almost like a tree shake for your code. It forces you to remove unnecessary stuff from your code base. Because you can't write tests for things that are unnecessary. Because you tested something, and you test the same thing with another if, and it's left over from some refactoring, or you didn't really think it through completely. And your mutation testing will say, what's that thing? And your answer is, I'll delete it, it's fine, right? So it can actually, it makes your code like just so, in a strange way, that feels weird even after having done it for like 6 months or years. It's surprising. So that's an added sort of advantage, right? So at TryOptima here, we've done it on the following libraries. These are the open source libraries. So TryStruct, TryToken, those both, and TryDeclarative, those three have 0 surviving mutants right now. Query, form, table have many surviving mutants. They're just bigger, just takes forever. And I'm not gonna sit for like a month doing that. It's not fun. But doing it an hour once in a while before I go home is good. Right? So, any questions before the live demo? Shoot, you've already asked me some questions.
Seems like you could use this as a pass criteria for hardcore test-driven development course.
Really hardcore. Woo! Yeah. Let's see. Can you see anything? No. So I've already installed whatnot on this thing. So try-cache memoize is a nice library Percival wrote a while ago. So we're just going to start the mutation testing. You see it's going to count up the kills in the beginning. It's going to take about a minute. And see you already got some survivors. And then you can do this. You can open up another window and you do if I can type, show the results. It's going to say these are the ones that survived. These are, we haven't gotten to them yet, and then we can show one of them like 40, like that. Looks like that. Well, that wasn't very interesting, so we'll probably whitelist that one. That was a little bit more suspicious. Why can we do that? I'll ignore it. It's not very interesting. Yeah, that's a classic one. We don't check our exceptions properly, right? There's a lot of code in our test suite where we do to take we have PyTest, right? You do with this is going to throw an exception. You get the exception thing back, and you do if the string of the exception contains, and then some part in here. I'm like, yeah, but I can add stuff at the ends. You can. It's a very tiny hole in your test suite. Another one. Wait, what did it do there? Another one. Who cares? This one is a bit more suspicious. It's like, why can I just throw away the function? Like, it takes a key function. So this is a Python implementation of this thing. So it's a memoize thing, and you can pass in a function that calculates the key for the cache, right? And I can throw it away. Just throw it on the ground, and it's fine, apparently. So we'll just apply that on disk. And oh Jesus! Oh, change the font size. Can I? Yeah. Can anyone read that? No. How do I change the font size?
Control plus.
Oh, I disabled Control plus because I typed it by mistake. There we go. So, where did my mutation go? It's not the right file. There we go. So, look at that. Key func equals none. Nope. Okay, so obviously we don't have a test for using the key func feature at all. It's just, we just don't have a test for it. So that should be easy, right? Oh, this is very boring old school tests, but just write a test. So you should be able to write a test for that. Test key func. What's we gonna do? We have a function, memoize, Okay, why isn't fine? The foo, it takes some variable, right? And the default implementation here is going to be like this. You do foo1, it's going to be 1. Oh, sorry, return better. And 2, it's going to return 2. That's the default implementation. Okay? Because the key func is just take all the arguments. Come on. Import this name. That one. Okay. No? Object is not callable. Silly. Silly thing. There we go. So that's the default behavior, right? But what if we do this? Key func equals lambda of the something, I don't care, and do let's do this. I don't care what the signature is, but I'm just going to return 7 or something.
Missing a B.
Yeah, the da. There we go. Now this will fail. But yeah, see, that works. Revert the thing. Right, so if I don't have the change, this should be like this now, right? The default behavior before was it uses the variable input as the cache key, but this is what it should be doing if I do that. But with the mutation active, it still passes y. God damn it. Why would you? I saved, right?
You selected on 1 on 7, right?
I could be 1.
It should be 1. Because that's just the cache key.
Okay, so
Yeah. So it should be returning the same value over and over again. Come on.
The correct memorize?
It's the right one, right? Func, key func.
Did you have to?
Self-memorize, maybe.
What?
Was it a self-memorize?
That's not the one at least.
No.
Scroll down a bit.
Yeah.
Well, that's something else. That's for self-memorize is for classes. So you do it. Then it uses the self as the cache key. This is the most boring part of everything. Like that. This is fairly straightforward. Why doesn't it work? Oh yeah, I know why. I know why. Look at this. Look at this is what the mutation. Yeah, it's using the C implementation. Because it's very annoying. This is the problem with using Python in your Python library. It's very, very annoying. Where is it? I want to kill it. Does anyone up at the top of their head know where the Python binary is? I think I can get the file.
That's memorize.
No, not that. Not myself. Print? Print? I didn't get print. Yeah, here we go. No, it still thinks that's one.
It's being smart.
Is it?
Try to
Like,
trick
it's gonna import that thing. Yeah, it imports that thing. But I want to. Yeah, it's. Oh. Free.cache. This is the worst demo ever.
Rename the
from
Python version.
Memorize 2.
Good thing we're recording this.
Yeah, great. From try cache memo is import under file as foo. Print foo. That thing has to be the C Python. No. Ah, damn it. I don't know anymore. In any case, make sure that you kill the Python implementation before testing this library.
But the map is running the Python version, because otherwise you wouldn't have all the surviving mutants.
It does. Why? Ah, that's right. How can it do that? Then it's gonna, it should. Not code changed. Yeah, this actually finds mutants. Otherwise it should always be survived.
Is it a Python?
I guess you make the decision somewhere which implementation to use.
Huh.
That was an exercise.
Yeah, now everything fails because I wrote this little thing that does this. Huh. Yeah. Anyway, yeah, let's undo all the things and do the cache and yeah, I don't get it. It should be running. Notepad does not run the C version because then everything would be surviving all the time. Anyway, I'm gonna cut my losses here. If you don't have a Python implementation, this is much nicer to work with. So, thank you.
I think one of your competitors does Python.